Hey there. In this video, we're going to talk about a very interesting concept in Meridian, the open source MMM solution from Google, which is knots. So every open source MMM model out there, like Robin, for instance, has some sort of very unique characteristic or unique feature. And knots happens to be Meridian's most unique feature. In the case of Robin, it was decomped RSSD, which is a very specific kind of accuracy or error metric. But more to the point of Meridian, why am I talking about Meridian? First of all, now it has become extremely popular. This was only launched in the early part of 2026. But now Google has recently announced that within the enterprise edition of Google Analytics, which is GA360, Meridian is actually going to become integrated, which means that Meridian is going to become even more mainstream, becoming more and more available to marketing operators and not just a specialized team of experts or data scientists. So what is this knot really, and why am I really interested in it? So knots is nothing but time effects. So if you're going to look for a counterpart in frequentist approach, then it would probably be dummy variables to understand the effect or to model the effect of any special events or occurrences in time, like seasonality or any kind of promotions, something like that. So it's the nearest concept available, but it's also not really just dummy variables. It's something different than that. So it's time effects as Google is defining it. And in order to understand the time effects, they've also brought in the concept of baseline. So essentially, it's contributing to the baseline. So what is the baseline at any given point in time? So to understand this, I've created this sort of a quick walkthrough kind of an app.
So what you see in front of you is basically called the mu curve. So this mu is actually what goes into the final model. And I can just show you here. If you look at this final model here, that Y obviously stands for different time periods and for different geos, because Meridian can also be a geo model. So they obviously have different components like the ad stocks and the for the different media variables, and then you also have for the reach and frequency for spend, as well as for reach and frequency you also have other kinds of variables. But this mu t and this tau g, we're going to come to that tau g a little later, but this mu t is basically what goes into the model, and that is actually something that includes the concept of knots. So it's a little complex, and this is precisely why this equation, and more importantly how the connection of this mu and knots or knot values, as we will see, and how you can actually set priors on them. This entire thing was a little convoluted, and it was a little complex and completely unknown. Obviously, as you understand, like I said, it's unique to Meridian. They have come up with this concept. So to jump back to that overview tab once again, so mu, how it actually evolves over different time periods for different knot values, this is what we're going to see. So before jumping to that curve, these are the three objects in mu. So mu is given by a matrix multiplication, really, which is first of all the weight W, and then another entity B, which is basically the knot values, really. So the weights will be simply what will be the weights that will be given to a particular knot in order to understand the value of mu for any time period. So if you want to understand what I'm trying to say, if I click on any of these points here, you will see that there are different time periods, and you'll see that any time period will necessarily obviously be between any two knots. So that's how it's always going to be calculated. The weight given to the left and the right knot of that particular time period multiplied by the knot values, that will basically give this of course multiplied not in an algebraic sense, but or not in a simple linear algebraic sense, but in a matrix multiplication format. So this is a dot product or dot matrix multiplication that will give you your mu values for the different time periods. And what is interesting is this always lies on a straight line, and this is basically the concept of linear interpolation. So all the mu values between any two knots will always be on a straight line. So basically what Meridian is trying to do in this by introducing the concept of knots is your entire phenomena, right, your response curve or your revenue curve, and how it is basically moving together with other variables like media variables and other external variables, other confounders or covariates, how it is basically moving with that over time. It's breaking down each time period and conceptualizing different knot values. So it also goes on to recommend that you can have knot values to at every given time point, and that will basically give the baseline amount of revenue at any given time period. But obviously that's going to be too much. So basically, if knots is given by k, then k becomes equals to t being the number of time periods, but k is generally going to be lesser than t, and therefore this acts actually as a dimensionality reduction problem or a dimensionality reduction feature. So if you are from data science background, you must already be aware of what I mean by dimensionality reduction. There are plenty of methods there. PCA is often used for dimensionality reduction or principal component analysis. So it's that sort of a point, because the number of a time period t is obviously going to be that's going to add to the number of dimensions. But if you use k, it's going to become a feature which will be a much lesser number, because you're not going to have not at every time period. So when it's a national model, Google actually recommends that you have that. But in case of geo models, because the number of data points increases by the number of geos, it suggests that you can actually have lesser number of knots there, or at least sometimes even if there are a lot of geos, then maybe even one knot. But if it's one knot, it will simply be 1 point, and it's going to pass one single line basically passes through it, so it's going to be a constant value. So we're going to see that once more, but this is the overall concept. For anyone who wants to get a quick overview of what knots really is, I've already actually walked through the main ideas, but this mu is very central, because that actually goes into the model equation, and w, the weights and the b values are knot values. They actually form the matrix multiplication which gives you your mu. So let's actually see how you get the value. So the knot values actually comes from the model itself. So like I said, this is a Bayesian approach, right? So the Bayesian approach has something called a posterior distribution, if you're aware of it. Like there's a prior and a posterior. So the posterior distribution also has to be sampled from, and that sampling approach, there are multiple approaches to sampling, knot sampler being one of them. So the knot sampler is basically what ultimately helps us get the b values. So the b values is something that we'll get from the model itself. The weight of each knot time period. So like I said, like because there are two knots on either side of each time period, you're going to give weights, right, to each of these knots, and that is calculated from the knot positions. And the mu values are ultimately also calculated because of the matrix multiplication given by w dot b. You can also use something called AKS. So by the way, this distance is called L1 distance. Essentially this approach of measuring the distance of each time period from the neighboring knots. We're going to see what I mean by that. But if you don't want to use this, you can also, this is for this understanding will help, especially if you use manual values of knots, or you choose to decide how many knots you really want to have. But you can also go for AKS, which is automatic knot selection. So that feature is also available within Meridian. So this is how the matrix really looks like. So it's 20 cross 1 for mu, and 20 cross 5 for the weights, and 5 cross 1 for b. And I think that's kind of obvious, because for weights, obviously you have a weight for each time point as well as for each knot, and you only have the 5 knot values for the individual 5 knots that you have. So the resulting matrix is obviously going to be 20 cross 1. Let's actually jump into each of these components now. So the knot values, like I said, is ultimately going to be provided by the model itself. So it's the values are obtained from the knot sampler. This is the underlying curve for the curve that we have taken for the mu curve, and each knot's value is sampled from this curve. So when we switch, it only changes k but not the shape, but that's just for the curve that we have used to understand the mu curve really, and how the sampling is being done. And so that's the question again for dimensionality reduction, or you can say the prior on b white actually acts as a regularizer. So why estimate b and not mu directly, right? So because b has only k parameters instead of t equals 20. So that's what I was saying, like you basically have a dimensionality reduction component to it. And it is somewhat analogous to the smoothing spline concept as well, and the lambda that's used there. So if you are familiar again from a data science domain, or from whatever background you have, if you are familiar with splines, this is actually a case of spline. Mathematically speaking, knots is a spline, but it's not exactly a smoothing spline. There are some differences. I'm not going to go into that, but it's basically a piecewise linear spline if you're interested. 10 functions also, you can say. So this is how the prior, because everything gets priors, right? So knot values, like I said, that's basically what is really knots, and mu is basically a term which is constituting the knot values as well as the weights associated to the knots, the neighboring knots to any time period. So the actual prior values are set on the b values, so that is you can consider that as being normally distributed, with the mean being at 0 and the variance being sigma b squared. Let's now go to the weight. So the weight is calculated using that L1 distance concept, like I was just mentioning. So for each of the left and the right knots, very simple idea. You can see, just take a modulus, or just take the absolute values of the difference in the time period for the different knots that you have already chosen, and the difference from that to any time period that you are choosing. So the weightage comes really from this sort of a formulation where, as you can see, you're dividing it by the sum of the two distances, and then you take the individual distance for that specific knot. For instance, for the left one, you take that's how you take the different ratios. And this is the sample rows from W really, and this basically is important to understand, like how actually the weight matrix really looks like. Remember, it's a 20x5 matrix. So if we look at t equals to 1, for instance, where we did have a knot, suppose, and for this, the weight value is obviously, the point is, if you take that very point where the knot is existing, so therefore the weight is going to be 1 there, right? There's no division of weightage between left and right. And 1.2 is, suppose, the value that we get for b, the knot value from the model. So mu is obviously going to be 1 multiplied by 1.2, so 1.2. Similarly for t and 4, obviously we can get the weights in this case, which is 0.4 and 0.6, and suppose we have a certain b value at t equal to 6, we get 2.008. so this is how we get the different this is how the weight matrix is basically constituted. Every row gets at most 2 non-zero entries, you can understand, because obviously either it's going to be either on that specific time period where there's already a knot, or it's going to be one which is between two, so there's only one left and one right. So every row in the weight matrix is going to have like 2 non-zero entries, and the rest are going to be zeros. So just to sort of we're going to actually confirm that during the row walkthrough, so we can already take a look at that. Like for instance, W1 or for W4, in each of these cases, whatever is getting calculated on the basis of the weights, the weight ratios, and of course, like ultimately for mu as well, like we have the b values for each of the individual knots. But if you look at the mu calculated once, before we jump into that once more quickly, the mu is basically the actual time effect. So that is the net time effect that we are trying to capture, that Meridian is trying to capture, and that actually accounts as a baseline, right? And that is calculated as as a, like I said, a weighted matrix. So it's a weighted matrix multiplication, and this is how it's looking like. The total weight is always going to be 1. If you see from here as well, it's always 1, the sum total, right, in any row. So that's obvious. So weight here and 1 minus weight here, that completely makes sense, right? And this is obviously multiplied by the b values on each of the either knot positions. And if you look at any row walkthrough, I think by now it should have already been clear. So weight 1 for this particular row in the weight matrix, you obviously have only one non-zero value, because that's there's no weightage on left and right, and you just multiply it by the b naught, the knot value or the b value to get 1.2 to get mu. And similarly for here, you obviously have 2 non-zero entries because you have the 2 weights. You multiply them by the corresponding b values at the knot positions, and then you get your ultimate mu value. So that's basically what you're doing. This is basically the concept of interpolation once again, which ultimately gives us this straight line over the mu curve. So that was a quick explanation, because it's a lot of math, and hopefully the major concept was already clear by now. This is a boundary case and another edge case basically, and this is where if you have chosen knots such that you have also time periods outside of that zone, or outside of that range where you have got the initial and the last knot values. So for instance, if you have knots at time periods only ranging from 3 to 14, then at t equal to 1 and 2 and t beyond 14, say from 15 to 20, there you're obviously going to have like you don't have knots, right? So then you have to clamp it to the nearest position where there was a knot. So b3, for instance, at t equal to 14, that is basically where the weightage is going to be 1, right? Because that's what you're going to clamp it on, and which means that simply the mu is going to be equal to that not value there. So whatever is the not value, so the not value here is b3. And similarly, before 3 t equal to 3, you will be clamping it to the not values, because w is going to be 1, and you're going to clamp it to that particular value, which is b1, basically at t equal to 3. So before first not clamping, after last not clamping, and obviously on the knot we also know that it's going to be similar, right? And anything in between two knots is going to follow the method that we have already seen, so there's going to be an interpolation. So this is just to say, like, this is basically a specific boundary or edge case.